In the last video, we summarized the basic electromagnetic phenomena needed to understand how electrical machines operate. Now we can delve into the fascinating world of electric motors.
There are basically three types of electrical machines. These are DC motors, synchronous AC motors, and asynchronous AC motors. For all types, these machines are in fact energy converters. They convert electrical energy into mechanical energy. This is what we call a motor mode. They're also capable of so-called generator mode, where mechanical energy is converted into electrical energy. We've already had an insight into the world of DC motors in the Crystal Clear Electronics curriculum, so now we'll just refresh the knowledge we gained here. In these types of machines, a conducting loop, usually a coil, is placed in a constant magnetic field and the current is passed through it. The current-carrying conductor interacts with the permanent magnetic field, which exerts a force on it. This causes the rotor to rotate around the axis of the motor. Using the right-hand rule in the diagram, you can see that the force is acting downwards on the left side of the loop and upwards on the right side. The rotor is fixed around the shaft, which forces it to follow a circular path. The rotation of the rotor does not reduce the magnitude of the force on the conductor, but it does reduce the distance of its line of action from the axis, so the torque on the conductor loops will also be reduced, to such an extent that at 90 degrees, the torque is eliminated. At this point, however, the commutator is in the process of reversing the polarity of the supply voltage to the conductor loops so that the direction of the current and the direction of the force will be reversed, meaning the torque will again be applied to the conductor loops. A similar process takes place at the 270 degree position, and from then on, the process repeats periodically.
The stator can be made not only of permanent magnets, but also of electromagnets. We can talk about external, series, or parallel DC motors, depending on how the stator windings are powered.
We'll not get into details of the advantages and disadvantages of the different excitation modes. It's enough to know that in the case of externally excited motors, the stator windings must be excited by a separate power supply. In contrast, in the case of series and parallel excitation motors, the stator windings are connected in series or parallel with the rotor windings inside the machine.
It is important to note that the single-phase AC motors used in power tools and kitchen appliances are actually DC motors with series excitation. These are called universal motors because they can operate on DC or AC power.
The motors described so far were all equipped with a mechanical commutator. With the development of semiconductors, it became possible to extend the range of electrically commutated motor types. These types of motors were needed for several reasons. A major disadvantage of brushed DC motors is that an electrical arc, more commonly known as an electrical spark, is generated between the carbon brush and the commutator when the connection is broken. This rules out their use in mines and other places where this spark could cause a fire. In addition, carbon brushes wear during use, and because of the fine dust they generate, they cannot be used in places where high cleanliness is required. A further disadvantage of brushed motors is that the rotor can heat up considerably due to the current flowing through it, and cooling this can be difficult in thin air, meaning in low air pressure. Examples of these problems include the space industry, where engineers have had to develop a DC motor that can be used in the vacuum of space, so it doesn't overheat, and one that can be used in oxygen-rich environments, so one that doesn't cause sparking, used for mixing the oxygen tanks of spacecraft, for example, and without pollution, so without the fine dust produced by carbon brushes.
In the 1960s, the development of semiconductor technology opened the door to brushless DC motors. Without these devices, man would hardly have reached the moon.
Brushless DC motors are also known as BLDC motors for short. In BLDC motors, the rotor is a permanent magnetic part and the rotating magnetic field is created by external coils. This is done using what is known as electrical commutation. As shown in this simplified diagram, the stator windings are evenly distributed around the rotor. During electrical commutation, Switches are used to drive these coils one after the other with direct current and then switch them off, thus forcing the rotor magnet to rotate continuously. Let's look at this in reality. BLDC motors are preferred on drones because they fit in small spaces. Technically, this is the motor we are talking about. It's a typical drone motor with 300 watts. I'm not going to disassemble this one right now. We'll show you some closer pictures of it because you can see the internal structure very clearly without disassembling it. These little gray parts are basically the magnets, and the coiled part is shown here. This motor is a bit strange because if you look at it, the part that rotates with the propeller is actually the magnets. So the rotor is now on the outside, it usually would be on the inside of the motor, and the winding of the stator, which you can see here, is attached to the drone. So that's basically how it's structured. It's a very beneficial feature of this special design, and that's why they're so popular in drones that you can practically see through the whole motor, so the air moving through the propeller is practically blowing through the coils and can cool very well. This results in the engine's cooling being solved when it's operating.
I don't see any electronic commutator in this.
You're quite right not to see it because it's not there. Actually, there are only 3 wires here. To be honest, I don't like to classify BLDC motors as DC motors because they are not really DC motors, but 3-phase synchronous motors with proper motor control electronics. So you still need a motor controller to make them rotate. You can see that, as I mentioned, this one only has 3 wires. For some reason, when talking about BLDC motors, we think about both the electric machine and its controller as a whole. Perhaps this is because in many cases, the electronics are built into the motor housing, such as the 12-volt fans used in computers. Apart from this minor naming quibble, BLDC motors have several advantages. For example, only the stator needs to be cooled, as the current that generates the torque flows in the stator windings rather than the rotor, so only the stator windings are heated. It also does not contain a mechanical commutator, which would create sparks, wear and tear, and pollute the environment. Another advantage of electrically commutated motors over mechanical ones is that they are more efficient, meaning they convert electrical energy into mechanical energy more efficiently. One of the obvious reasons for this is that they do not contain carbon brushes, which cause losses through friction, and the current conduction properties of the carbon brushes are below the same parameters of an electric commutator.
Stepper motors are also part of the group of electrically commutated DC machines, but with this type, the developers did not focus on uniform rotation and uniform torque output, but on picking up predefined discrete positions, angular rotations, with minimal error and maintaining these discrete positions.
The principle of their construction differs from a general BLDC motor in that the stator and the rotor are usually toothed, as shown in the figure. If a voltage pulse is applied to one of the motor's windings, the motor's rotor will jump forward one tooth at a time, called a step, hence the name of the motor type. If you connect pulses to the stator windings in the correct order, the motor will start to rotate and will take the number of steps corresponding to the pulses. If the voltage is left on a particular coil of the motor will not rotate but will hold the position. The number of degrees the motor will rotate in response to a pulse depends on the winding and the gearing. The value of this parameter for a given motor type can be found in the datasheet.
There exist electrical machines that operate not on AC but DC voltage. An example for those are the asynchronous motors.
They get their name from the fact that the speed of the motor shaft is not synchronous with the speed of the rotating magnetic field. They are also known as induction motors because of the way they work. They are very popular because, among other things, of their simple construction and the fact that in many cases the motor can be connected to the mains without a controller, such as in electric lawnmowers. Asynchronous machines are also made up of two main parts, the stator and the rotor. In all cases, the stator is made up of coils, that is electromagnets, and the rotating magnetic field is created by the alternating current flowing in them. Depending on the construction of the rotor, two types of asynchronous motors are distinguished. One is called a squirrel cage, the other is called a slip ring. In the case of the squirrel cage design, the rotor is basically made up of rods held together at both ends by grooved iron plates. It resembles a squirrel cage, hence the name of the motor. This construction is a very simplified short-circuit winding. It's a lucky coincidence that there's a squirrel cage asynchronous motor right in front of me, but you may not see it yet. If I take hold of the rotating part and pull it out, well, things will practically pop out and you can push the rotor out of here. So you can probably see some similarities to the figure I have just shown. We can see here that this would be the stationary part. Here's the winding, so this is the wound design. And if we look inside, we will notice that there are actually iron plates that are basically placed next to each other, and these coil bundles are pulled through them. So this would be the stator, but what's really interesting here is the rotor, which is a squirrel cage design. Here, we can see that there are bearings. This is more interesting from a mechanical point of view. Maybe Rebecca would find this aspect particularly interesting. At first, it might seem strange that you don't see any rods. The reason for this is that for such low power motors, typically in the range of a few kilowatts, a different design is usually used because it is cheaper. Practically, what we're talking about here is that we can see different colored regions. This darker colored part is basically the outer part of the iron plates. So these grooved iron plates are put together, put into a mold, and the whole thing is cast with aluminum. Basically, the iron plate itself is designed so that the aluminum flows into the grooves and they become the conducting rods that basically form this rotating winding. And finally, there's a ring of aluminum on both sides. And that basically short circuits these aluminum rods. So, it's the same type of squirrel cage design rotor we've shown in the picture, but it's much easier to manufacture.
In a slip ring motor, not only the stator but also the rotor is made up of coils, the windings of which are connected to a so-called slip ring. These are connected to resistors, through which the current flowing in the rotor windings is closed. By using different values of resistors, the characteristics of the motor can be modified. But before we explain this, let's get better acquainted with the operating principle of asynchronous machines.
Asynchronous machines work on the principle of self-induction. The rotating magnetic field of the stator induces a voltage in the rotor. In a squirrel cage rotor, the cage of the rotor is a short-circuited coil, while in a slip ring rotor, the rotor windings are connected by resistors. In both cases, the induced voltage causes a current to flow through the rotor. This causes the rotor to have its own magnetic field, which interacts with the magnetic field of the stator to exert a torque on the rotor, so the motor starts to rotate. It's evident that the rotor of an asynchronous motor cannot rotate at the same speed as the rotating magnetic field of the stator, because then induction in the rotor would stop, and so would the torque. The frequency at which the stator's magnetic field rotates is called the synchronous frequency. It's equal to the quotient of the frequency of the three-phase AC excitation and the number of pole pairs.
The number of pole pairs is usually indicated by a letter P on the motor's data plate. This parameter results from the winding design of the stator, and that is all we need to know for now.
Suppose you're given a motor with a datasheet that says the number of pole pairs is 2, and you want to run it from a 50 Hz mains supply. The synchronous speed is, therefore, 25 revolutions per second, or 1500 revolutions per minute. This means that the motor will spin a little slower than 1500 RPM at idle, due to the minimal losses in the bearings and air resistance, which we need to overcome with a bit of torque. This figure shows the speed-torque curve of a typical asynchronous squirrel cage motor. It's clearly seen that the starting torque of the motor is much lower than the maximum achievable torque, the so-called stall torque. ML shows the curve of a typical load. At the intersection of the two curves are the nominal torque and the nominal speed at a given load. At this torque and speed, the motor stabilizes. In general, an asynchronous motor can always be operated stably between the tipping point and the synchronous speed. The motor's current speed curve shows that the machine draws a lot of current from the start to the tipping point, which puts unnecessary strain on the winding, the motor supply lines, and the electrical network.
This starting problem can be eliminated by using a slip ring motor. With this type, a resistor is connected to the rotor's terminals at startup, which can be changed to a lower value after a certain speed has been reached. This way, the starting current drawn by the motor will be lower, since the current generated in the rotor is limited by the resistors.
There are not only asynchronous but also synchronous motors as well. They get their name from the fact that the speed of the rotor is synchronous with the rotating magnetic field. The stator of these machines, like that of asynchronous machines, is a coil which, when supplied with alternating current, generates a rotating magnetic field. Part of the motor may be a permanent magnet or a DC excited electromagnet, or possibly a non-magnetized ferromagnetic material known as reluctance motor, but this type is not discussed in detail now. The rotating magnetic field interacts with the magnetic field of the rotor and rotates it. In DC synchronous motors, the rotor consists of a coil supplied by slip rings and carbon brushes. An inherent characteristic of this type is that it requires maintenance at certain intervals due to wear of the carbon brushes. This problem can be easily solved by using a motor with a rotor with a permanent magnet. These magnets are usually made from aluminium nickel cobalt or neodymium iron boron alloys, which are very magnetizable. The disadvantage of permanent magnet synchronous motors is that the magnet material makes them more expensive than motors with DC excited rotor. As I've already mentioned, the motor I have in front of me here, called BLDC, is itself a three-phase synchronous motor. However, there is a subtle difference in the design of BLDC motors and normal synchronous motors. BLDC motors are usually square field, while synchronous motors are sine field. This means that if you rotate the rotor of a sine field synchronous motor at a constant speed, the magnetic field at a given point on the stator will change sinusoidally. Similarly, the waveform will resemble a trapezoidal square waveform for a square field motor. You can easily find this out about a motor by looking at the induced voltage waveform between its two outputs as you rotate its rotor, since the induced voltage will be proportional to the change in the magnetic field.
A big advantage of synchronous motors is that they are smaller than their asynchronous counterparts with similar power and torque. However, they have the disadvantage that they require a motor controller, which is responsible for starting and reaching the target speed. Therefore, until the explosion in the development of semiconductor components, these types of machines were not widely used as motors.
Synchronous machines have been used as generators in power stations for a very long time, since the frequency of the voltage generated is directly proportional to the speed of the machine, which is essential for the accurate generation of the 50 Hz frequency of the grid.
We're running out of types of electric machines, so we can move on to the motor control. But you'll have to wait until the next video to see that. Stay tuned.
Bye!
Bye!